Hello.
Can you hear me?
Y entonces esto, yo la o sea, tengo que más o menos y le dije, dígame a escribir y me hizo simplemente el color, bueno, el color yo viene un poco más claro, más pero también es cierto que de pronto me empezó a comentar cosas.
Hello. Hello.
Okay. Now I hear you.
Okay, you can hear me.
Okay, now I hear you. Professor Balucani, can you try the microphone? Can you check the microphone? Can you try and speak? Professor Facinelli, can you check your microphone? Try and speak.
Yes. Can you hear me? Yes. Prova.
Yeah. We can hear you.
Okay.
So yes. It's okay. You can hear us. Yeah? Okay. Everything is okay.
Thank you.
Thank you.
Okay, now in principle, can you hear me?
Yes, we can hear you. Okay, everything is okay. So we can start whenever you want.
Ok. Fai tu, Marcio. Ah, perché inizi tu? Ah, sei tu prima, ok.
So I think that we can start. The first speaker of this afternoon session is Luca Mancini from the University of Perugia, and he will talk about. He will give a presentation titled "From Nitrogen WD Back to N2: A Theoretic Investigation of the WD plus CH2NH, which gives N2 plus CH3 reaction, and implication for the atmospheric chemistry of the titan." Luca, if you want, when you are ready, you can start.
Okay, if you confirm that you can hear me, I will put in
Yes, we
presentation.
can hear you. We can see your screen.
Okay, great. So,
Just the presentation.
okay. Thank you for the introduction. In this contribution, I will show you some recent results about the theoretical investigation of the reaction between atomic nitrogen and methanamine, with the focus on the formation of molecular nitrogen and possible implication for Titan's atmospheric chemistry. Titan is Saturn's largest moon. It's one of the biggest moons in our solar system, but in reality, it's the only body, except of our planet, to have a atmosphere mainly composed by molecular nitrogen. So the understanding of the chemistry taking places in this body can help us to elucidate the first step of the evolution of chemical species in our prebiotic planet. That's why different missions have been developed in order to try to understand the structure and the composition of this body and of its atmosphere. The structure of the body is composed by 5 major layers, with an inner one made by water-based silicate rocks, and other inner layer made by water and salty liquid water, with the outer part of the body composed by organic compounds, which is what gives to this body the typical orange color, which is seen from all the images from the mid-age. The temperature on the surface is around 94 Kelvin, which means that the water is water ice, and methane and small hydrocarbons are in the liquid phase. So, for what concerns the atmosphere of Titan, which is, as I said, mainly composed by molecular nitrogen, and of temperature and pressure varies as a function of the altitude. The region we are interested in is the upper atmosphere, in particular the thermosphere, at an altitude of around 1,000 kilometers, where the temperature is around 180 Kelvin and the pressure at 106 millibar. And in principle, these conditions can be considered prohibitive for molecular growth. But despite that, the recent missions a complex chemistry taking place, leading to the formation of a series of molecules, also from a periodic point of view, and different molecules with the ratio between carbon, nitrogen, and hydrogen atoms of around 1:1, which means the complex chemistry taking place involving nitrogen and nitrogen-emitted species. So the main scheme concerning the chemical activity on Titan's atmosphere starts with the activation, let's say, of the most common and most abundant molecules, such as molecular nitrogen and methane, through different energetic sources, including ultraviolet photons and energetic particles coming also from Saturn's atmosphere, which interacts with the molecules and leads to the formation of reactive species, which then can interact and react with other molecules present in the atmosphere and lead to the formation of more complex molecules, also important from a prebiotic point of view. Finally, new and important information will be delivered by the NASA and Dragonfly missions, which is scheduled to departure in 2028, and will give us plenty of information about the rich and complex chemistry of this body. As we said, the most abundant species is molecular nitrogen, which has a high chemical stability. So the chemistry is driven by the so-called active nitrogen, which represents a series of atomic, molecular, and ionic species which are activated through different sources of energy, and in particular the interaction of molecular nitrogen with ultraviolet photons and energetic particles is the formation of atomic nitrogen, both in its ground state, which is the 4s state, which is not reactive with shell molecules, and atomic nitrogen in the first electronically excited state, D, which has a long radiative lifetime, and then high energy content. So this means it's particularly reactive and important for nitrogen and titan. And if we look at the abundance of atomic nitrogen as a function of latitude, we can see that around 1,000 kilometers, the concentration of the abundance is quite high. So this is the perfect for reaction. The other species we are interested in is methanamine, which is considered the intermediate for protein chemistry, since it contains this double bond, which is important from a prebiotic point of view, which since it's present also in amino acid form. The presence of methanamine in titan substitution has been suggested by the investigation, but despite its relevance, the current photochemical models tend to overestimate the main formation route is the reaction of atomic nitrogen with alkane, but there are still missing destruction route. And the reaction of methanamine with atomic nitrogen may, in principle, represent an important destruction pathway for this species. That's why we decided to study the reaction of methanamine with atomic nitrogen, computational protocol, which used for the analysis of cellular reactions, starting from the first investigation of the potential energy surface at the level, with the literally functional and triple zeta resistant for thermodynamization and harmonic vibration of frequency equations, followed by a more accurate analysis, energy analysis at the couple cluster level with the same triple set. First, before deriving the full potential energy surface, we focused on the initial approach, the capture approach, and we decided to investigate the energy of the process to evaluate the presence of a barrier transition. So we performed a series of scan calculations, which represent a series of energy calculations with an increasing distance between the nitrogen, the atomic nitrogen, and the CN double bond. And as we can see from the energy profile, the energy tends to decrease towards the formation of a covalently bound intermediate without the presence of an energy barrier. But the capture process is barrierless, which is one of the key points for the reactivity considering the Higgs conditions of Titan's atmosphere. Temperature and pressure are quite low. It's important that the reactions are barrierless and exothermic. So we investigated the potential energy surface, focusing on the chemical pathway leading to the formation of hydrogen. And as we can see, we have, as we saw before, the barrierless approach, the attack of atomic nitrogen to the CN double bond of the molecule, leading to the formation of the initial covalently bounded intermediate named N1, the potential energy surface. Once formed, this intermediate can isomerize to a barrier to its structure through the breaking of the carbon-nitrogen bond. And we have also the presence of two isomeric forming 2 and E3, which are connected by this barrier, which indicates also the delocalization of multiple bonds in the C and chain of the intermediate. Finally, the transfer of an atomic hydrogen from nitrogen to carbon can lead to the formation of the last intermediate identified in the potential energy C4, in which we can notice the presence of a CH3 molecule, and the subsequent and quite easy fission of the CN bond leads to the formation of molecular nitrogen together with the The combination of tones show an ion intensity of around 638 at couple cluster level, and all the stationary points, including all the transition states, lies below the reactant energy asymptote. So the reaction is globally exothermic, and this is another important point for the feasibility of this process from Titan's atmosphere. Here in the slides, you can see the geometries that we obtain from the reactant products and all the intermediates in the potential energy surface, with the bond length in angstrom in blue and bond angle in orange. And we can see that the attack of atomic nitrogen leads to the formation of the first intermediate, N1, where the atomic nitrogen attacks the skeleton of the molecule and leads to the breaking of the carbon-nitrogen double bond and the formation of a new nitrogen-nitrogen bond in a cyclic structure, which can be then broken, and finally the hydrogen transfer leads to an increase of the CN bond, which is then easily broken leading to the formation of molecular nitrogen. So the entrance channel show a barrierless interaction, as I said, of atomic nitrogen in an efficient capture process under tight atmospheric condition, and it's a bit different with respect to other investigations that we did in the past, considering the same reaction of atomic nitrogen, different molecular partners such as acetonitrile, and cyanoacetylene, all molecules containing CN, but in this case, the atomic nitrogen can, in principle, attack the CN of the molecules leading to the formation of new and unexpected reaction pathways, but the presence of transition state, which can lie more below the reaction energy asymptote, leads to a reduction of the reactive flux. So the attack is not favored with respect to the attack of other side molecules. In this case, in the case of the methanamine molecule, the weaker stabilization of the CN double bond forces somehow the interaction of atomic nitrogen with the CN bond, enabling the formation of molecular nitrogen. For what concerns future step of the work, we are currently analyzing a study of potential energy surface of the process, which is more congested than that I showed before, but we can see the different hydrodynamic formulas of the forms of the which has been identified, but most of the barriers which connect various minima, so which drives the formation and the isomerization processes are quite high, so are higher with respect to the one we saw before. And this in principle leads to a less favored reaction channel with respect to the one related to this. The only other must be taken into account is direct dissociation and direct hybridization from the first intermediate identified in the potential energy cycle, should take into account the competition between the formation of molecular nitrogen and the formation of atomic hydrogen together with the related co-fragment, which can still maintain the cyclic, the two-membered cyclic form or the linear structure, depending on which isomers, which minimum potential energy surface under elimination. That's why it's important, together with the refinement of the potential energy surface, it's important also the analysis to arrive at constructions and to understand which are the most important product channel in the reaction. So, in conclusion, we performed a theoretical investigation of the reaction between nitrogen and methanamine using a combination of TFT and carbon cluster calculations. The reaction starts with the barrierless attack of atomic nitrogen to the CN of the methanamine molecule. We identified the potential energy surface a series of isomerization processes characterized by transition states which lies below the reactant energy asymptote. So the channel is very exothermic and feasible under tight atmospheric conditions. We want to demonstrate that the reaction can be a feasible way for the methanamine molecule, which is currently overestimated in the photochemical model. So this can be an additional route which leads to decrease the abundance of these molecules in the models. But we need to complete a full characterization of the potential energy surface, including competitive hydrogen transfer processes, and determine the branching ratios through an RRKM approach to understand which are the possible products of the reaction. With this, I concluded. I'd like to thank the organizing committee, all the member of my research group, and of course you for your attention.
Thank you, Luca, for your nice presentation. We have time for some questions, consideration. No question means that everything is clear. Thanks again, Luca.
Thank you.
We can move to the next speaker, which is myself. Seleziona diretto che è X26 e file maggiore di presentation version 2. Possiamo passare quella su PowerPoint. The next speaker is myself. We will remain on Titan since we talk about some reactions of nitrogen X excited WD state and processes aromatic hydrocarbons. But I will present these reactions from a computational point of view. Let's start the presentation. Andare avanti.
Forse ti conviene stare di là, ma forse come pensi che è meglio.
Dispositivo per controllare da remoto.
Ma se può mettere lì, sì. Io ce l'ho il computatore.
I will talk about a study performed in the University of Perugia about the reaction of nitrogen with polycyclic aromatic hydrocarbons. Nitrogen in its excited WD state. The synthesis of nitrogen containing organic molecules is a crucial step in prebiotic chemistry, as they are potential precursors of important biological molecules, such as amino acids. In this respect, the interaction of nitrogen in its excited WD state with hydrocarbons is particularly interesting because nitrogen in its excited WD state is particularly reactive. Interestingly, simple species containing nitrogen have been detected in the interstellar medium in the upper atmosphere of Titan. As we know, Titan is the main moon, the massive moon of Saturn. It's characterized by low pressure and low temperature. The surface temperature is indeed under 100 Kelvin degrees. The main constituent of the atmosphere of Titan is the nitrogen, molecular nitrogen, and small hydrocarbons. But there are also benzene, toluene, and the orange haze. This atmosphere is particularly interesting and has been the object of many investigations because it is reminiscent of the primordial atmosphere of Earth. Molecular nitrogen and methane, for instance, through the energy provided by sunlight or energetic particles, can react and give rise to to complex organic molecules, and at the end also toluenes. And the problem is that nitrogen in its molecular form is characterized by a strong bond and is difficult to chemically fix in compounds. But the observation of nitrates in trace amounts indicate that some forms of active nitrogen are produced by several processes, for instance, energetic UV absorption, electron impact, and so on. These energies indeed can excite the molecular nitrogen to excited states which can be dissociative and can produce atomic nitrogen not only in its forest ground state, but also in excited states, in particular the WT, which is very reactive and is characterized by a very long radiative lifetime. So this species is particularly reactive, and this is the reason why we are interested in the reactions where it is implied. We studied in the past the interaction of nitrogen in the excited WD states with aliphatic hydrocarbons. Now we want to extend this study to aromatic hydrocarbons, which are present in the titan as well as in the interstellar medium, in particular polycyclic aromatic hydrocarbons. Most of the time we start our study from an experiment in Perugia. We have a cross-beam molecular apparatus which can allow the study in a single collision condition, a study of the reaction between a molecular beam source, in this case the hydrocarbons which we want to study, and atomic beam source, in this case the nitrogen. The experiment then must be supported by a theoretical study. In particular, we study usually the potential surface of the system of the reaction of interest, and we use this information to compute the rate coefficients, which it can be employed, can be inserted into the kinetics modeling. Of course, it's necessary to have rate coefficients very accurate, and you can obtain this coefficient only if also the potential in the surface is computed at a very high computational level. This is our computational approach. First, we study the stationary point that is minima in transition state of interest, performing density functional calculations using basis set of at least kappa zeta plus polarization plus diffuse functions quality. Then we refine the energies of the stationary points, performing accurate calculation as couple cluster with single, double, and triple excitation including the perturbativity, and again with basis set of high quality as the RCC VGZ. However, also these calculations present errors because of the basis set incompleteness. So we perform also a complete basis set extrapolation, including also covalent correlation effect. These calculations are very accurate, and we can estimate the error to be smaller than 5 kilojoules per mole. However, we will see that these calculations cannot be performed on very large systems. This is the reason why we explore the possibility of using the onion approach. Let's start from the reaction nitrogen in its excitability state and benzene. Here we have a simplified version of the paths of this reaction, where the main exit channels, it is the one leading to the formation of hydrogen cyanide, the one leading to the formation of acetylene, and those leading to the formation of hydrogen with different co-reactants, co-products. Sorry. This surface has been computed at the couple cluster CBS level, so very accurate level. Let's focus our attention to the lowest exit channel, that is the one leading to the formation of hydrogen cyanide. Here we have reported this part of the surface, and the energies have been computed at different levels. In particular, the first value is relative to density functional calculations, Bitterlip calculations, with a triple zeta basis set plus polarization plus diffuse function. The second value is couple cluster calculation with the same basis set. The third value is couple cluster calculation with extrapolation to the complete basis set, inclusion of the core balance correlation effects. The last value is very accurate, as I said before. We can notice that there is discrepancy between couple cluster computed with a triple zeta basis set and at CBS level. It means that even with a triple zeta basis set with polarization and diffuse functions, we still have an error relevant due to basis set incompleteness. From these values, we can notice that sometimes there is a better agreement between the FT calculations and couple cluster with complete basis set extrapolation. However, this agreement is not systematic, so is not really very relevant. For nitrogen plus benzene, for this reaction, we are able to perform couple cluster with extrapolation to complete basis set. This means performing couple cluster using quadruple basis sets, and so calculations which are very heavy, both from computer time requirements and storage space disk. So for the system, it's still possible. It was still possible to perform this calculation, but for more complex systems, this is not possible anymore. But our aim is our goal is to study polycyclic aromatic hydrocarbons interacting with nitrogen. In particular, we start from the reaction between nitrogen and naphthalene and phenanthrene. Here we have the same exit channel, the one leading to hydrogen cyanide of the reaction, and plus naphthalene. For this system, it was still possible to perform couple cluster calculations with the CC PVZ basis set, but not, it wasn't possible to perform the extrapolation to complete basis set. But also couple cluster with a triple zeta basis set applied to the whole system was an extremely cost approach. So we decide to try a different approach. That is the only approach where only part of the molecule is described at a high level, and the rest of the molecule is described at a lower level. This consideration derives from the fact that if we consider the naphthalene and the nitrogen interacting with naphthalene, on the right there is the first intermediate when nitrogen WD interact with naphthalene. We can notice that only the ring interested in the interaction is affected. The other ring remain almost equal to before. So we decide to study the ring reacting with nitrogen at a Kaplan-Meier level, and the other ring, the spectator ring, at the FT level. Here we have a reported stationary point, and we can notice that the spectator ring is almost does not participate to the reaction. And we can, from NWD plus naphthalene, we can see that the onion calculation, the onion results, most of the time are very close to the couple cluster with the triple zeta basis set calculations. So this suggests that the onion approach can be acceptable. We extended our study to the reaction nitrogen, WT, and phenanthrene. And in this case, again, we noticed that only the ring interacting with nitrogen participate to the reaction, while the other rings act as spectators. In this case, it wasn't possible to perform a Kaplan-Meier applied to the whole system. So we were able to perform only onion calculations. Of course, as we see before, considering nitrogen and benzene, even the Kaplan-Meier calculation with the triple zeta basis set contain a significant error due to basis set incompleteness. But at this point, since the reactions are very similar, at this point we can use the N plus benzene calculations to estimate the error due to complete basis set also for the reactions on N plus naphthalene and N plus phenanthrene. And here we have reported again the geometry of phenanthrene and the interaction with nitrogen, the first intermediate. Again, the two side rings remain almost unaltered, so they do not participate in the reaction, as we can see also from the other stationary points. At this point, we can suggest a best estimate for the potential distances of nitrogen, WD, and naphthalene and phenanthrene, considering the only results and adding the correction for complete basis set for the completeness of the basis set computed with the benchmark calculations of nitrogen plus benzene. So this is the best estimate for the pass of N plus phenanthrene. So we can suggest that this approach can be used also for to study the reaction nitrogen WT with more complex polycyclic aromatic hydrocarbons. We already started considering N plus coronine, but we can go even further, since the difference in the cost from the reaction nitrogen WD plus benzene and nitrogen WD plus other polycyclic aromatic hydrocarbons is small because the rest of the molecule is described in DFT calculations. I would like to conclude thanking, acknowledging the financial support of the Italian Space Agency to the project Migliora and the Italian Ministry of University and Research to the project Thermopylae and Solstice, and all of you for your kind attention. So I have concluded. Of course, if there are questions or curiosity, I am.
Maybe it's an question.
Yes.
You performed complete basis set limit extrapolations.
Yeah.
So triple and quadruple set. You use double and triple.
And quadruple.
And quadruple.
Yeah.
Yeah, because with double and triple, the results are fantastic. Yeah.
So we consider a couple clusters. We are double theta, triple theta, in quadruple theta plus polarization plus diffuse functions. And of course, the calculations are then we use the extrapolation method of Martin, which is and with all those calculations we more proper. And then we have below to balance the correlation effects, considering a couple of classic calculations for but only CCSD, not because applied to all the electrons of the system, even the correlations.
Because I was surprised in the calculations I showed for the eximers for this, that the doubly augmented basis set in this case is free of basis set incompleteness errors. It was surprising. I don't know if you maybe you could try with doubly augmented basis set to see if the same happened for this kind of studies. It's expensive, but it's not so expensive.
Calculation converge very slow.
Yeah.
The problem.
Yeah, but it was surprising to me that doubly augmented the out basis sets correct out the problem of the existing ingredients. I don't know. Thank you.
No. So we can, I think that we can move to the next speaker. Making a virtual presentation.
Can you see the slide, my screen and the slide?
Not yet.
Oh, good. Thank you.
The next speaker is Stefano Faccinelli from the University of Perugia, which will do a presentation titled Production Characterization of Channel Affecting ions by synchrotron radiation. Now we can see your presentation.
Thank you, Marzio. Thank you.
Thank you.
Can you hear me?
Yes.
Okay, thank you. Thank you, Marzio, for the kind presentation, and let me thank also the organizers to give me the opportunity to present this contribution at the ICCSA conference. My talk concerns essentially an experimental studies of the dissociative double photoionization of cyanoacetylene, that is a molecule of importance in astrochemistry. By using the ultraviolet synchrotron radiation, we studied the molecular dication formation and the fragmentation following the double photoionization of such a molecule. This work is the result of a collaboration between the universities of Perugia and Roma La Sapienza, together with the IOM CNR Task Laboratory of Trieste and the Synchrotrone Trieste Area Science Park. In general, our studies are aimed to characterize molecules that are of interest for interstellar medium and planetary ionospheres. In such a concern, it has to be noted that a very important characteristic for the chemistry of such molecules is that they can interact with electromagnetic waves such as gamma and X-rays and also ultraviolet light. So the UV photochemistry studies can be performed by using an intense and tunable light source as the synchrotron radiation. In general, UV light photons have enough energy to ionize molecules, producing both singly and doubly charged ions. In this latter case, we have the so-called molecular dications. What means molecular dications? It means doubly positive charged molecular ions. They are in general formed whenever a system has available a lot amount of energy, as for example in the flames. And we can find this kind of ionic species in low concentrations in many natural plasmas, such as planetary ionospheres, interstellar clouds, and comet tails. And indeed, you can see in the right part of this slide the nice picture of the Hyakutake comet that was discovered in 1996, and the astronomers found in the comet tail many single and doubly charged ionic species. In general, molecular dications can be stable, unstable, or metastable species in gas phase. This depends for the simplest case of the diatomic dications by the parameter here indicated as delta parameter that was introduced first by Bates and Carson in 1955. The beta parameter, the delta parameter is defined, as you can see, as the difference between the second ionization potential of the atom between the two bonded that is less electronegative. In this case is the B atom. And the first ionization potential of the other atom. When the delta parameter is negative, we have the formation of a stable, thermodynamically stable molecular dication. On the other hand, when delta is very positive, we have an unstable species. And there is also a third case that is very interesting for us, and this happens when the delta parameter is almost zero or slightly positive. And this is the case of the formation of a metastable species. In this case, we have the formation of a species which can live a certain period of time before its dissociation into two single charged fragment ions via the so-called Coulomb explosion process. Such a situation can be also represented using the potential energy curves diagram that is reported on the left part of this slide. And for us, it's very important and very interesting the case of the production of metastable dicationic species. In fact, the first to be interested to the nature of these ionic species was Linus Pauling in 1933. In fact, he published this interesting paper performing valence bond quantum mechanical calculations on the simplest diatomic dications, that is helium-2 2+. As you can see in the right panel of the slide, Pauling showed that the simplest such a simplest molecular dication is metastable with a lifetime of about 220 minutes. And then it dissociates into two helium plus fragments with a very high kinetic energy content of about 10.2 eV. On a more practical level, other authors have been interested in these species as possible candidates for energy storage. In fact, for example, in 1989, Nicolaides has proposed helium-2 2+ dications as a possible source of propulsive energy based on its high energy content, low weight, and relatively long lifetime. Our research group started from 2001 to produce and characterize molecular dications through double photoionization processes with synchrotron radiation. The experiments are carried out at the two beam lines, gas phase and CIPO, of the Synchrotron Elettra facility in Trieste. And during the time, we have studied several dications, as you can see in this slide, many of which are of great interest from an atmospheric and astrochemical point of view. They are the dications of nitrous oxide, the carbon dioxide dications, the propylene, the nitrosyl chloride, the allene dication, and finally, we have studied also the cyanoacetylene dication. For all these species, we were able to determine the energy threshold for their formation, their lifetime, and the kinetic energy released of the possible fragment ions formed after the Coulomb explosion process. For such a purpose, we exploit an ion position sensitive detector coupled with the ARPES angle resolved photoemission spectroscopy end station located at the gas phase beam line of ELECTRA in order to perform electron-ion-ion coincidence measurements. On the right part of the slide, you can see a picture of the ARPES and the station used in our experiments. In this slide, you can see the main part of our experimental apparatus used in order to perform both electron-ion coincidence measurements. On the left side, scheme of the experiment up, while in the right part of the slide, you can see a picture of a device. Now we move on to analyze recent see we have studied that is the cyanide molecule. Cyanacetylene is the simple, the earliest organic molecules interstellar medium, and acting as a two larger molecules, including nitrogen-containing aromatics. In general, cyanacetylene is not commercially available, and for this reason, its experimental characterization, especially from a spectroscopic point of view, is difficult. For this reason, we have developed a specific synthesis procedure for cyanacetylene based on the suggestions by Miller and Lemon, and the scheme of our synthesis is illustrated in this slide. The double photoionization of cyanide has been studied by using UV photons with an energy range between 30 and 50 eV. On the left panel, you can see the coincidence plot at a photon 45 eV, while part there is a mass spectrum recorded same photon and highlighting in red the peak related to the cyanacetylene molecular dication formation. Very quickly, I can show you the 9 fragmentation processes recorded in these double photoionization experiments with the related energy thresholds. Furthermore, also a preliminary evaluation of the relative abundances of the various channels was also performed. And then finally, in our first analysis of the recorded data, we were able also to show you a precise evaluation of the lifetime of the molecular, of the threshold energy formation for the cyanacetylene molecular dications. And we measured a threshold energy of 31.4 eV. Finally, I can tell you that our data are also in progress. The analysis of our experimental data is work going on, and we are confident that with our technique we can able to extract from the data also the relative cross sections of all observed fragmentation channels as a function of the photon energy, and also the kinetic energy released for the formation of each fragment ion. I thank you very much for your kind attention.
Thank you, Stefano, for your presentation. Question, curiosity. You are very clear because to start. Thank you again, Stefano.
Thank you to you. Thank you.
We can move to the last feature of this session, which is Nadia Moncani from Perugia University. In Nadia, we talk about, we give a presentation titled Can OSIS be formed in the interstellar medium? A computational investigation with the OH plus SIS reaction with a kinetic analysis. Nadia, you are there?
Yes, I'm here. At the moment, I cannot succeed in sharing the screen. Just 1 second.
Right.
Okay, I saw that you were doing it properly, so you have to go to the share button and then select your entire screen. Okay, now we can see your screen. So now you can open the presentation. Okay, you can see it.
Okay, thank you very much.
You're welcome.
Okay, thank you very much for giving me the opportunity to present, even though I'm not there, and there is always some problem with a remote connection. So today I'm going to show you some results that we have obtained in collaboration with my colleagues. Some of them are there in the room in presence. And this time we will speak about a very different kind of systems. You see, no organic chemistry here of any kind, because I'm going to tell you about our study on the reaction OH plus SIS. This reaction is of relevance to the chemistry of the interstellar medium, not planetary atmosphere as this case. Okay, so let me just introduce the topic a little bit. So silicon and sulfur are abundant actually elements in the Milky Way. Of course, not as abundant as hydrogen or oxygen or carbon, but for instance, silicon is the 8th most abundant species, and sulfur is the 10th most abundant species. They belong to the sequence of stellar nucleosynthesis, the alpha sequence, and so that means that they are easily formed by stellar nucleosynthesis until, of course, the stars dies and then release in space all the elements that have been synthesized. They can form a diatomic molecule, SIS. This molecule is actually very common in the interstellar medium. And it's a molecule characterized by a strong multiple covalent bond with a dissociation energy of 620 kilojoule per mole. And it belongs to a family where you put together an element of the carbon group and the oxygen group, but of course is not as stable as CO or SiO, and not even CS. Yet it's a very stable molecule. So as I said, this species are relatively common in different interstellar environments. So for instance, it is very typical of the circumstellar envelopes of late AGB stars. So this is a very important region for the interstellar medium because it's the place where dust particles are synthesized. and silicon sulfide can help in the process. But then they have also been seen in protoplanetary disks. So this is the place where actually new solar systems are formed. So this is a star dying, and instead we have the formation of a new star with the surrounding planets. And it's also very typical of this particular environment in the interstellar medium, the so-called shocked regions. These are again associated with the formation of new stars when the star is very active and it ejects strong solar winds and other jet of particles that they impinge on the surrounding gas. And in these cases, it is possible to release all the refractory species. Silicon is a refractory species, of course. Actually, it belongs part of the silicate particles that are formed in the circumstellar envelopes of dying stars. But in these particular environments, after shock waves, these species can be released in the gas phase. Now it is very clear that silicon in a space is essentially depleted from the gas phase because it enters into the refractory matter. But in this region, silicon is then released in the gas phase. At the same time, it is not so clear what happens to sulfur. So sulfur, there is a kind of mystery about the main reservoirs of sulfur in the galaxy. And so this kind of molecule where you see both the presence of silicon and sulfur are very interesting because they can help us to pinpoint somehow the sulfur inventory. Okay, at the moment, to date, silicon sulfide remains the only molecule where we do see an SiS bond, but there are many other molecules that have been proposed to be present, like for instance HSIS, and more recently also OSIS has been proposed. So there have been investigation of the rotational characteristic, rotational spectrum of this species, because this is of course necessary to try to detect them remotely through rotational spectroscopy. And for the moment, there is not any clear detection of SIS, silicon oxysulfide, but there is an upper limit in a very famous region, Orion KL, where we do see many of these species emitted. So according to these estimates, we are an upper limit. So we know that there is at least a ratio of 20 or something between the abundance of SIS and OSIS. But even though there has not been a clear detection so far, yet there have been suggestions about its possible formation. And for instance, the first suggestion was the reaction with atomic oxygen. But unfortunately, this route cannot be active in the context of the interstellar chemistry, because you would need to stabilize the first addition species, and this is of course not easy in the case of the interstellar medium because of the very low number density. So that means you cannot have stabilizing following reaction or three-body reactions. And since there is a very exothermic channel for the triplet potentially surface, then of course it is not possible for the species to be stabilized. So because of this, we thought that maybe a best reaction, much better reaction, could be the reaction with the OH radical, SIS plus the OH radical. Why that? Because we were inspired by other reactions, for instance, the reaction of OH with CO, OH with SiO, and also OH plus CS. You see, again, we play a little bit with the periodic properties of elements, where silicon behaves kind of similar to carbon, and sulfur kind of similar to oxygen. Of course, this similarity has some, you cannot apply, simply. And so there are a lot of investigation, especially in the reaction with SiOs, which is strongly related to our case, because in our case, we have SIS and form, therefore not a symmetric species, but OSIS. So there are experimental and theoretical investigation, for instance, in this reaction. And so we see that the reaction is not very efficient because the rate coefficient is around 510 to minus 12. So that means that the reaction can occur in the condition of the interstellar medium, but is not so effective. And if you look at the energy profile for this reaction, it is immediately clear why. So there is the the exit channel is slightly exothermic, so that means it's not very efficient. But not only that, a more thorough investigation actually was able to pinpoint that there is the formation of a van der Waals complex in the entrance channel, and then there are barriers, internal barriers to overcome. These are submerged barriers, so that means they are below the reactant asymptote, so the reaction can occur. But of course, this is a kind of problem because you can have a back dissociation from the initial addition van der Waals complex. So that's why the rate coefficient is not so called gas kinetics. Gas kinetic means that every collision will become a reactive collision. The situation is a little similar but different with respect to the case of OH plus CO, because in this case, some of these barriers are emerged. So that means that really, in this case, it is more difficult to promote a reaction, as in fact this is a very well investigated system because of its relevance in combustion chemistry and atmospheric chemistry. Okay, so by drawing a similarity, we decided to try the reaction between OH and SIS, and these are our results. You see the global potential energy surface in this first image, where you do see two sets of energy values. So the black one are DFT calculation using the omega B97 XD functional. In blue, you can see couple cluster with the CBS value. So these are more accurate, of course, as we just had just a few minutes ago. Okay, so let's analyze how the reaction works. So the OH, the atomic oxygen, the H radical can add either to the sulfur or the silicon side of SIS. The situation is very different in the two cases because, as you can see, the addition on the silicon side is much more efficient because it brings to a very stable intermediate. Or addition on the sulfur side instead brings to this very weakly bound species that in all cases, even if they are formed, the main fate of this species would be to isomerize to the same intermediate that is formed directly by the O addition to the silicon side. So either we start with the addition on the sulfur side or silicon side, the structure, which is indicated here with min1, will be the most, the only actually intermediate which is formed by the different addition. Then starting from this first intermediate, we can have different pathways actually leading to SIS plus H, the molecule we are interested in. There are actually three different possibilities. So we can have the direct dissociation of min1, but as you can see, you need to overcome a transition state which is very high in energy. So the channel is open, but of course it's not competitive with channel 2 and channel 3 because they are characterized by a much lower transition state. Then you have the formation of other intermediates, like for instance, this trigonal structure that can only evolve towards the OCIS molecule. Then in this other pathway, we have the formation of an isomer. So you can see just the hydrogen atom has went from the oxygen to sulfur. And then you can still have the formation of OCIS plus H. But in the most favorable cases, the formation of OCIS is actually in competition with another channel, which is much more exothermic and also easy to achieve without any significant barrier. And in this case, the products are SiO plus SH. Okay, so of course, we need to run kinetic calculations to understand which is the most favorable channel, which is the different contribution of all these pathways to the global reaction, and these are the results. So as you can see, at very low temperature, but these are the temperature of relevance to the interstellar medium, and up to room temperature, the channel leading to SiO plus A, so the competing channel, is actually largely dominant. So the channel leading to OCIS is only accounting for 16-18% in the range of temperature. As you can see, there is a trend with the temperature. So if the temperature will be higher, so probably the flux, the reactive flux leading to SIS is going to increase. Okay, just while we were doing all this calculation, a paper came out, another group characterized the same reaction, the OH plus SIS, and also in that case, they had in mind the possible formation of OSIS, and the calculations, the results are very similar to our calculation, even though there are some pathways that are missing, but the main pathways are there. They did not perform a kinetic analysis. However, by simply looking at the general profile, they evaluated that 25% of the of the reaction can lead to OSIS. So this is a little bit larger, but this is just an estimate. It's not based on kinetic calculation, like in our case. So as you can see, it's a little bit larger than the real value. So you can see in this table, which is also present in the conference proceeding paper, that actually the results are in very good agreement. So there are small, tiny differences that are compatible with the accuracy of both methods. And okay, there are some points missing, as I said, in the potential surface of Costa et al. In a way, the most significant difference in between the two potential surfaces calculated by us and by Costa is actually related to another process, the reverse reaction, H plus oil the OSIS molecule. So if OSIS is ever formed in the interstellar medium, its most probable fate would be to react with hydrogen if the reaction is feasible, because atomic hydrogen is the most abundant species in all conditions. So the question is that if you look at our potentially surface, the reverse process, so H, the reaction between H and OSIS in both cases, okay, in our case, we always have a transition state to overcome. But while in this case, I mean, the pathway that brings, in this case, to the trigonal intermediate, well, as a matter of fact, the transition state, which is related to this pathway, is submerged. So that means it's slightly below the energy of the entrance channel of the reactants. So that means that there is probably a van der Waals complex somewhere here that we didn't locate, and then you have this transition state. In the case of the Costa et al. Calculation, there is no barrier at all to go to the same intermediate, the trigonal intermediate. And that encouraged them to propose this value. This is a gas kinetic value for the rate coefficient, because they were considering the reaction totally barrierless in that specific pathway. But as we said, in the case of when we have this van der Waals complexes, we saw that in the case of the OH plus SiO reaction, so normally you have a significant back dissociation component. So this value is probably too large. So as I said, this is probably the main difference between our potential surface and theirs. So not as far as the reaction OH plus SiS is concerned, but about the one of the other possible reaction that for which we obtain information from our potential surface. Okay, so these are the conclusion of this presentation. So differently from the case of the related reaction with CO, SiO, and CS, the hydrogen displacement channel leading to OS or OSIS plus H is not the dominant channel, where it was dominant in all the other cases. The formation of SiO plus SH is largely dominant. It accounts for more than 80% up to the room temperature condition. And therefore, this reaction does not preserve the SiS bond in most of the reactive flux. So there is a portion, less than 20%, that is actually preserving the SiS bond, but not most of it. That means that actually the OH radicals joins atomic oxygen, because this was already known, as an effective agent to transform SiS in SiOs. This has very important implication for the relative abundance of these two species that was seen to change a lot with the different conditions characterize interstellar regions. So this will be explored in astrochemical models to see if this reaction, together with atomic oxygen, is able to explain the strong variation seen in the ratio between the abundances of these two species. And then further investigation is needed to assess the OSIS resilience with respect to the reaction with H atoms, because of the abundance of H atoms in all the interstellar contexts. And so it is very important actually to try better investigate further if there is the presence of this van der Waals complex, and also to perform a kinetic analysis, because the presence of a van der Waals and of a transition state which is submerged but very high in energy can strongly reduce the rate coefficient of this reaction, which has been proposed, as we saw together, to be gas kinetics, but probably it will be not as such. So I would like to thank the fundings received from this, essentially from these two projects, and of course I'd like to thank you for your attention.
We have time for curiosity questions. No, there are no questions. So again, this means that you were very exhaustive and clear. So thanks again. We have finished the session. We can thank all the speakers again.
Bye bye to everybody.
Bye bye.
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 Io le vado a dare la mia.
Goodbye to all.
Allora, la mia presentazione. Andrea. Micro. Okay. Excuse me. Yes.
Okay.
Now it's okay?
Yeah.
Okay, sorry. Okay, is this? Okay, so I was speaking about this work in collaboration with a PhD student about the study of perovskite materials. You know that perovskite materials have emerged as one of the most exciting classes of materials classes about photovoltaics. Okay, so this is okay again. Okay, so the photovoltaics, the perovskites, has this general form ABX3, where normally the A is an organic cation, typically methylammonium, or Fa, that is formamidinium. Okay, B is a metallic cation such as lead or tin, and X is a halide anion, typically iodine, bromine, or chlorine. Okay, that is the normal structure of perovskite materials. So the A site cation, is coordinated to 12 X anions, so iodine, bromine, or chlorine, forming a cubo-octaedron. Okay, while the B site cation sits a six-fold octaedral coordination environment. So, if you think that this structure makes a perovskite so unattractive in their remarkable rise in power conversion. So I don't know, you know that the PCE, that is the power conversion efficiency, starting from 3.8 in the 29 until to this year increase of the lab scale until 26.7%. So obviously, it puts this type of materials in a direct competition with the commercial silicon solar cells. Okay, because the perovskites are low cost, is a solution processable, and then that is they have a high absorption coefficient across the wide wavelength range. So that is the pro and cons of the perovskite materials. What is the problem of this type of materials? The problem is the long-term stability. For the reasons, it's not a material that can be competent with the normal commercial silicon solar cells. Okay, so what is the problems of the stability of the perovskites? The problems are the degradation factors. The degradation factors, the main factors of degradations are the moisture, the UV radiation, the temperature, and the thermal stability. The thermal stability is the main, very important degradation factors of the perovskites, because during 20 minutes at 100 degrees is the composition, and at 200 degrees move completely to PbI2. So that were studied from the XP experimental studies. So how we can change it. From the experimental part of view, several mitigation strategies have been proposed that you can see here: compositional and energy engineering, additives, interfacial engineering. So this collaboration started because that I will show now. When you add a small amount of an additive, and they can observe that the perovskite modifies the properties. So more stability is not affected for the moisture, UV radiation. So we have a thing. We can try to use the CO2 like an additive in the to add to the perovskite. Okay. In other way, what the CO2? So the CO2, you know that the CO2 can be reduced on perovskites through photocatalysis. Obviously, rising atmospheric CO2, if we can use the perovskites to absorb the CO2 from the atmosphere, is a double green. In this case, because the perovskite material is used to substitute the commercial solar cells, and plus absorb the CO2, the huge amounts of CO2 in the atmosphere. The problem is that the reaction mechanisms are not fully understood. So for this reason, we decided to do the first step to study how is the interaction, the long-range interaction between CO2 and the perovskites. So we have observed that determines that the weakly bounding are a precursor states and give us information about the reactions pathway. Okay. So our colleague ran the calculations for the ab initio methods DFT using quantum espresso. That is the characteristic of the calculations, and they evaluate the stability of the perovskites with the additive to obtain the final absorption energy. They develop a protocol that they have a library generation about all different perovskite structure. After that, move to a machine learning screening and arrive to the refined DFT calculation with quantum espresso, obtained the optimized structure. Okay, so that is our perovskite. So methylammonium, lead, and iodine. So the slab is formed by 408 atoms, 4 layers with 40 lead, 112 iodine plus 32 methyl ammonium. That is the full layer. The PBI2 is terminated, and the MI terminated surface are studied in this way. We have 3 layers rigid, so fixed, and we have the 2 more external layers that are relaxed. So consider all movements about bonding and so on. So because that is species absorption, not chemical absorption, and we needed that the more realistic way for the more external layers. Okay, so this group studied more than 80 additive molecules to observe the absorption energy. Okay. with the quantum expression. Here they started this is a list of the most important, I reduced the list of the most important additives. In this case, to evaluate the absorption energy, previously evaluated the perovskite distortion energy, molecular distortion energy, and the contact energy. Obviously, for us, it's important the absorption energy that is decomposed in contact energy, molecular distortion, and the perovskite and additive terms. Okay, so you can observe that if the additive has a functional group that contains the amino group or sulfonated groups, produce the strongest interaction with the absorption. So we move from minus 0.90 to 1 minus 1.87. That is the first group of calculations. After that, they move to another type of groups of additives. I put one of these, sodium acetate, and the dimethyl phenetyl sulfonium iodide. That is, and the phenethylammonium iodide. And observe that increased again the absorption energy. Obviously, it gives that the NH2 and SO3H groups strongest perovskite interaction. So the absorption energy more negative. At this point, we have that is the last additive, that is the family of the ketosane. The family of the ketosane, the ketosane salts give a bridge with 2 lead ions, give a no band gap states. It implies that the absorption energy is more negative than the previous additives. Okay, so at this point, we decide to study if we can consider the CO2 like an additive for the 2 reasons that I said previously. So that is a slide that presents about the problems of the that is move there, the global greenhouse gas emission, and that is the papers of the reference that has started to study the CO2 like photocatalysis. So I don't know why. Okay, it's different. Okay, so our idea is from the quantum express, the colleagues give us the atomic charges. We define the use our potential to the force field to define the non-electrostatic potential that all of you can know. We apply the periodic boundary conditions and we run the molecular dynamics. After that, these molecular dynamics were classical molecular dynamics were compared with the absorption energy running from the quantum calculations. The important part in this case is that we have used the improved Lennard-Jones that you can know, and we have used the DL poly potential. Okay, so here I put the important characteristic of the DL poly. We run the NVT ensemble classical molecular dynamics with a cover nose thermostat, that is the box, the dimension of the box, with periodic boundary conditions. We run into 10 Kelvin, the temperature 10 Kelvin, 1 atmosphere, equilibration 1.5 nanoseconds, and a production of 5 nanoseconds. Here, I would like to put the parameters that were developed to introduce in the improved Lennard-Jones molecules, improve Lennard-Jones semi-empirical potential. You know that we need the well depth, that is for the pair interactions, carbon lead, oxygen lead, carbon ion, oxygen iodine, carbon X, where X is like consider the methylammonium, our organic molecule, and oxygen methylammonium. The beta parameter were set between 6 until 8, depending of the different pair interactions. We're running these classical simulations, and after that we compare with the quantum, the DFT results. That is the last screenshot of the DFT results. You can observe our layer of perovskites and where is put the more optimized CO2. The absorption energy were evaluated previously, the total energy minus the perovskite energy alone, and in the case the CO2 energy. The absorption energy using with the DFT results, they have obtained minus 6.61 kilocal per mole. So we consider that a physisorption weak, no covalent interaction. We observed in this result how long is the distance in electrons for the interacting pair, carbon lead, oxygen lead, carbon iodine, and oxygen iodine. Obviously, we observe scanned the CO2 above the sites of lead and iodine, and they rotate over 20 degrees to evaluate our different configurations. We have observed that the oxygen iodine is a good key descriptor of absorption geometry. That is for the DFT results. After that, we're running the classical molecular simulations. Here we put the representation of the configurational energy versus simulation time. We can observe that there is a small fluctuation, are not considered, like at more or less minus 12 kilocal. So around the 10 Kelvin. The 10 Kelvin are the temperature that we want to maintain for our calculations. Obviously, it gives us an idea about that the parameters are well suited for this system. So that is the first indication. The parameters describe good this system. Okay, that is preliminary results. That is the last snapshot of the classical molecular calculation. You can observe that in this case, the CO2 is in a different orientation respect of the DFT calculations. Here I put the interacting part that used it in the improved Lennard-Jones potential, and here that is the final distance with the DFT and with the classical molecular distance. So the distance that we have measured from the molecule CO2 to the first layer in this case, and to this point that is our methyl ammonium. Okay, so here we can observe for the case of the oxygen, of the CO2 and the iodine, for the DFT, the distance is almost 3.79, and with classical molecular dynamics is 3.93. We can see that is an excellent agreement. Instead, the interaction energies is a little difference. Remember that with the DFT we have found 6.61 kilocal, but the molecular dynamics we found 11 kilocal. So we can see that is the same order of magnitude, but we think that the difference of this energy, now we are working in this way, is why we consider one center of the interacting for the methyl ammonium. So we are sure that when we defined all the interacting centers with the different groups of different atoms of the methyl ammonium, our force field will be described better, this absorption energy. So but so far, like a preliminary, we can say that the improved energies parameterized are specifically for this system. We can see that it's efficient and geometrically accurate. Okay, here we represent the radial distribution function for the oxygen, because it's a key descriptor, the oxygen of the CO2 respect of the iodine. We can see that we have a very primary peak at almost 3.76, and that is the most probable distance to the PC absorption. That is consistent with the DFT geometry and also with the classical molecular dynamics. We can observe also that there are secondary peaks at larger R, and that give an idea, if you remember, because the iodine, the contributions from iodine in subsurface layers, it gives us reflects the perovskite structure. Okay, so it gives us an idea that to validate it. So to conclude, we can conclude that to summarize that works, we can say that the DFT calculations, that we compare the DFT calculations with the classical molecular dynamics using the improved energies for the phosphorus. From the DFT site, CO2 absorb in the perovskite with this energy. The oxygen atoms are oriented toward lead and iodine surface sites, and the oxygen iodine distance is 3.79. Is a key descriptor. Instead, in the classical molecular dynamics, the geometry is agreed with the DFT. The energy is a little different, but because we have simplified the representation using one center, and the RDF, the radial distribution function, confirms that the order of CO2 arranged at Halid surface. We can also say that from the experimental part of view, the additive engineering, so for the calculations of the DFT with the additives, that the NH2 and SO3H groups are the strongest perovskite interaction. And for example, the ketosant salt has an absorption energy that is the more negative value that found so far. So I have finished. I would like to thank the group that the part of the group that ran the DFT calculations, and the other guys of our group. Thanks of you for the attention.
So we have time for a very short and conclusive. Anyone?
Yeah, I have one question. When you compare the distances for RDFT and classical, I understand the comparison with the distribution. Yeah, because the distribution is thermally averaged, no?
The RDF.
Yeah, and there is a good correspondence. But then you compare it with one frame, the last one.
No. The frame is only to show the last structure, or always only a picture. We compare the average, so the values is here. So the distance is the average.
Is it the average?
Yes. Yes, is the average during. No, only, sorry, maybe I explained it wrong. That is only to evidence that in the last frame, when we stop the DFT or the classical molecular dynamics, we have found different orientations, but that is the average. Yeah, is the average, obviously. Yes, sorry.
Okay, so thanks Maria again for.
Okay, thank you.
And the next speaker. Yes.
Are you ICCSA?
Yes.
So is that full screen mode?
Okay. I can use this for use.
The problem is that
Doesn't work.
work, but the problem is that
the...
it's a link. In the link there is is not possible see, but you can use to move the screen. Questa è la ragione per la quale è impallata lì.
Okay, so the next speaker is Andrea Lombardi, also from the Peruvian University. He's going to talk to us about the coordinate description clusters and biomolecules. Yes.
Okay, thank you. Okay, my contribution is about the idea of defining some invariant parameters to be used as a general tool for classification of molecular structures. Let me spend some words about the meaning of classification. There are so many meanings indeed, but the central idea of classification is okay. The central idea of classification is that you have a natural classification of a structure and molecules based on the chemical properties. Okay, for example, if you think about proteins, you have functions that each protein has, and so you can group proteins into classes on the basis of their functions, okay? So you have a number of classes. Now, the goal would be to find some parameters that induce a classification theoretically. So you observe the structures, you use your parameters, you apply classification strategies, and you obtain groups, okay? I'm sure you can obtain groups. Then you can match the natural classification with your artificial classification based on the parameters that you obtain. And if the matching is good, you can use this to make a connection between structure and properties, okay, which is the central goal of biochemistry essentially, but also in chemistry. You always want to know in advance maybe which are the properties of molecules without performing experiments or looking at them experimentally to save money because experiments are expensive. And this is actually the main purpose of theory, okay, to predict all the properties from calculations. So, of course, there are many ways to extract parameters, but I want to show you now how it is possible to define invariant parameters working on coordinates in a very standardized way. And let me show you some basic relations. Imagine you have a general system made up by m particles, atoms, okay? It could be a cluster of atoms, a molecular cluster, a molecule, small, large, biomolecules, DNA, proteins, whatever you want, also materials, if you want. And so you have a set of coordinates and masses. Starting from the position vectors, you can just scale them by masses in this way, and then you can arrange column-wise in a matrix 3 times n of dimensions, which is your position matrix. Now, everything from now on is about matrix algebra, and the goal is to extract high invariant parameters, which have to be, of course, invariant and not so many to simplify the picture. And one way to do that is as follows. If you think about this matrix, position matrix, you can let a rotation matrix, O3, act from the right, from the left, and this application performs rotations in physical space, okay? So you can rotate your structure without modifying the shape. But you can do also the dual equivalent of this operation. You can let a rotation matrix act from the right hand side on this coordinate matrix, and you still generate different structure, okay? This is not rotation in the physical space. They are called kinematic rotations, and you have to think about them as all the possible variation of the internal structure that do not modify the global shape of your system, okay? Why I can tell you safely that they do not modify the internal structure of your system? Because these two operations can be performed in a systematic way using the well-known theorem about matrices, which is the singular value decomposition, which states that any matrix can be replaced by a product of three matrices like this. Now, coincidentally, the two R and K matrices are exactly of the same type that we mentioned before. So a 3D rotation matrix and an n-dimension rotation matrix, okay? Right and left acting, okay? So this central matrix is our goal, because it is a 3 times n matrix, which is filled up by all zeros, with the possible exception of these three diagonal elements, psi1, psi2, and psi3, which are, by the way, subjected to this triangular inequality. These quantities are the singular value of your matrix, which means the singular value that you can associate to your molecular structure, essentially. There is, of course, the possibility to relate these quantities to the principal moments of inertia in this way, very simple way. And this is very general, okay, and can be applied to any kind of structure. So if you have 3D structure, you can replace it in a unique way, correspondence, with these three parameters, okay? These three parameters have a physical meaning, and they essentially take into account the global shape of your molecular structure. And also you can use this formula to obtain a square radius, which accounts for the global size of your system, okay? Now, there is a more deep meaning, of course, of these quantities, because speaking about dynamics, this replacement of your Cartesian coordinates by 3 external rotation coordinates and 3n-6 internal rotation coordinates plus this 3 size corresponds to a precise picture of the dynamics. And essentially, you can, I don't want to spend so much time on this because it is not the focus today, but believe me, if this decomposition can be results in a very nice decomposition of the energy of the system, because it is in terms of rotational energy, kinematic rotational energy, shape energy, global size energy, plus coupling terms, because these coordinates are not orthogonal globally. Okay, now let me skip this. I want to go fast. Just the physical meaning of the terms. The hyperradial, the raw energy, it's just the global rating of your system when you consider the dynamics. The shape energy, it is the energy that the system spent just redistributing the inertia, okay? So the global shape, how this evolves in time, if you consider the dynamics. Then there are rotations and internal kinematic rotation, which accounts for reactive processes, because this rotation actually describes vibrations, but also the exchange of particles, okay? So for example, if you have 3 atoms, A, B plus C. Using this coordinate, you can just perform the reaction from a kinematic point of view. So you can pass from AC plus B, okay, without variating the shape parameters, okay? So these size are really the highest level of invariance that you can extract from this, from any 3D structure, okay? Now, after this introduction, let me show you how in practice one can use these parameters for classification. So I told you that this is related to also the spherical symmetry of the system, and indeed you have these 3 limiting situations. So when the size are all equal, you have a spherical top, okay? When there is this inequality, you have oblate top, and of course you can have also prolate top. Using these quantities, you can find these deformation indexes, which accounts for the distance of your structure from the ideal spherical shape, okay? In this simple way. And of course, you can extract the size of the system. Now, let me show you a practical application with a very simple cluster system, which are Lennard-Jones clusters. These clusters are very simple because the kind of interaction is not very realistic, but if you consider many sizes of this system, you can use them as a prototypical system to account for many different chemical, physical and chemical phenomena. For example, you can study just the deformations, melting, evaporation, a lot of phenomena in a simple way. Now I consider here, for example, the structure, the minimum energy structure from 0 to 150. This is the number of atoms from 1, not 1, from 2 to 150, and I can show here the deformation, the trend of the deformation indexes, and the trend of the hyperradius. How can you comment this? The comment is that, for example, in this way, you can identify magic numbers here, which are the number of atoms for which the global minimum is a spherical top, okay? Which in cluster physics are known as magic numbers. And that's, you can identify them at glance, actually. Also, you can see the trend of the size, the global size, which is not linear, as expected, but you can see that you have some oscillation here. This can be useful for identifying, for example, outliers, okay? For example, here you can suspect that the global minimum is not the exact, the good one. You know that minima searching for a large system is a very computational demanding task. Okay, so it's not easy. So errors are common. I want to show you the same for larger clusters from 300 up to here 1,000 and I don't remember what it is. Sorry. 561, 3,300 from 661. And you can see that there is a similar trend with some structure that departs a lot from the spherical symmetry, but still you can identify easily magic numbers from these structures. And also you can identify this kind of strange behavior in the structure of the minima, for example, that maybe can suggest that you should refine the search of the global minimum, for example. No? And this is a very simple application, but we can just apply some more clever technique to find categories, clusters, classes of structures using, for example, the some standard classifiers that are used in machine learning application. I consider here the two very used ones, which is the k-means, which is an unsupervised clustering method, and also the mean shift, which is another unsupervised clustering method. The difference between these two, it is essentially that in k-means you have to supply as an input the number of our clusters, okay? So how many classes of structure you think that are present in your system, cluster system. With the mean shift, you don't need to supply this number. So the methods provides with the final number of different classes. In this sense, these two methods are complementary, okay? Because one, it is k-means theorem is probably more effective in clustering the data, but needs you to tell him how many clusters, okay? Mean shift is a bit less performing, as I will show you, but it provides the number of clusters, okay? Now, let me use these techniques to make this classification. Okay, these are the size values for the structures, 150 structures, classified by the k-means. You can see here that in order to obtain a meaningful classification, we need to set the number of clusters equal to 4. And it is not bad, okay? Because the clusters are enough well separated, okay? And although there is some apparent superposition, think that this is a 3D. So if you orient this, if you could rotate it, the classification is better than it appears now in this way. But now let me show you the second method, which is the mean shift, which provides the number of clusters. Mean shift tell us that number of clusters is not 4, but 3, okay? And it says 3, but you can see that the clustering is not so good because there is some compenetration of the clusters between each other, okay? There is a method, an heuristic method to analyze the data and locate the best number of clusters. It is the so-called elbow method, which it is a plot of the within cluster sum of the square distance, this quantity, as a function of the number of clusters. And the method says that the best number of clusters, it is where there is the change in slope. So in this area here, which correspond roughly to 3 and 4, okay? So there is no definite answer in this case, but the number of clusters, it is probably 4 because the k-means, this clustering method provides better results. Another application can be done similar on the deformation indexing, and the results, probably not surprisingly, are similar because k-means gives 4, okay, as a best classification, which is not bad, by the way, and mean shift tells 3, okay? Now, I can go fast, just showing the idea of how this method could be extended to biomolecules, for example, proteins. Everything of you know that proteins are sequences of amino acids, which can be thought of as 4 centers objects, okay? Because there is the alpha carbon, which is tetrahedron, and then you have the residue and H2 group, the hydrogen, and so on. So you can consider it as a tetrahedron. You can describe the tetrahedron as 3 vectors because it is possible to reduce to 3 vectors 4 atoms, and you can provide the size for each amino acid. So you can just replace your structure with n amino acid as a sequence, as a collection of n tetrahedron, which means n triple of size, okay? From this size, you can extract meaningful quantities, for example, a volume, which is the product, the surface, and the perimeter, and you can use these properties to classify proteins in machine learning application. For example, generating images like this. This is the plot actually of the covolume that you can obtain considering the product of the volumes, square roots of volumes, of two different residues in your complex structure. Usually, for example, for prediction of protein structure, they use the distances maps, which looks, for example, like that. This is the same structure, how it looks in terms of a graphic image using this covolume. Okay, this is just an example. You can use these images to feed the neural networks, no, in order to distinguish between different protein structure and properties. This is a different molecule, different protein, very different distance map, and also very different covolume map. It looks similar, but the density and clustering of lines is very different. Red lines and black and blue lines is very different. So this is a way that you can use to obtain in an very abstract way, but you know that in machine learning, it is not always clear the physical meaning of things, but protein prediction is largely based on images. No? You feed neural network with images, with plots, and this is an alternative way of depicting proteins in terms of these parameters. I didn't have time to use this with neural networks. It is a next development of this approach, but it looks interesting to me. I stop here, conclusions, and so we can conclude that invariant descriptors can be associated to any possible 3D structure, to any molecule, to any cluster, whatever you want. And deformation indexes are a combination of these invariant parameters. We obtained some exemplary results for Lennard-Jones cluster that induce actually some clustering of the different structure. Of course, there is much work to interpret it in a physical sense, but it is still a good result. And also, there is the possibility of applying this quantity, use this quantity with diverse possible machine learning methods and algorithms. Okay, so thank you for your attention.
So we have time for a short question. We have a curiosity. In the previous slide, in the other, the two, these are the covolume and distance for two molecules difference. For this protein.
See, this is this protein. Exactly this protein. I forgot to indicate the name.
And the next slide is for the other.
Yes.
But in the two cases, there is a diagonal in the distance.
Okay.
And what it means?
The distance is that because there are a diagonal means that you compare your residue, your amino acid with the same one. So this is not the important part. It is
because because in the next is the same.
Plot distance plot. There is always
it's okay. Is
by definition.
Okay.
Because the distance is it's lower, no? Okay.
I thought something of similar.
I have a question. Maybe it's a stupid question, but sure, it's a visual question. But is epsilon 1, epsilon 2, epsilon 3 parameters? They look like the eigenvalues of the inertial lesson, no? Because when you classify the structural prolate, etc.
No, there is a mapping because let me show you the connection. It is of course connected, but
yeah, because this classification can be done with this.
It is not exactly the inertial tensor.
No, I see. Okay.
Okay, so thanks again, Andrea.
Okay. We have finished. You can close or we close.
Thank you. We are concluding the session. Okay. Thank you for your attention.
Io devo fare, lasciare, sono sciolti, sono